Welcome everyone to the seminar today. Today I'm very pleased to have Professor John Methven from the University of Reading as our speaker. John got his PhD also at Reading, studying with Professor Brian Hoskins. He's now a full professor at the University of Reading. His research focused on atmospheric dynamics with focus on large-scale waves, cyclones, and high-impact weather. Basically, in both the tropics, mid-latitudes, and polar regions. So covering kind of all the tropics to the pole. John is now a co-chief editor of the Quarterly Journal of the Royal Met Soc and was also the co-chair of the WMO World Weather Research Program Working Group on Predictability, Dynamics, and Ensemble Forecasting. He's participated in field campaign as well as use model and observations to test theories and prediction. So I'm very pleased today to have him talk about the Arctic summer cyclones, a topic which is getting more and more important as we have global warming and the opening of the Arctic. And I know some of our faculty and students here are doing some research in the Arctic, and this is a topic that would be very of great interest to us. So without further ado, I'll let you take over.
Okay, thank you very much for inviting me. I want to tell you all about these Arctic cyclones, and this was part of a project which was originally instigated through, contacts with Stephen Cavallo in the University of Oklahoma and Jim Doyle at the Naval Research Laboratory. Because they started a program on Arctic prediction and they wanted us to take part in a field campaign. And I'm very glad they invited me to do that because, really it's been really exciting kind of moving some of our ideas of dynamical meteorology into the polar domain. And so there's a reasonably large team of us in the UK who've been working on this project. In particular, people at Reading and then the University of East Anglia, led by Ian Renfrew, who's been in polar meteorology for a long time, and then the team at the British Antarctic Survey. And then also we've been collaborating with the Met Office, European Centre, Met Norway, and then our colleagues in America and France. So it's been quite a journey, actually. And so I wanted to start with a motivation, why study cyclones in the Arctic and why focus on summer. And then I will talk about mechanisms for cyclone growth more generally, in particular coupling with the tropopause. And then I'll focus on characteristics of Arctic cyclones and these smaller scale tropopause polar vortices that you get in the Arctic. So some climatological work we did there, trying to understand what we might see during the field campaign. A lot of the focus is on the interaction with the surface in these systems. And so then I'll talk about some dynamics related to the effects of friction on those systems, which was done by a PhD student working with me called Hannah Crode. She's just coming towards the end of her PhD now. And then I'll tell you all about the field campaign that we actually did, not last summer, but in summer 2022. So we're still working on the findings from that. So the motivation, I'm sure most of you have seen this plot before. This really shows a huge decline in Arctic sea ice extent at the annual minimum in sea ice extent in September. So the bold black line is from the NSIDC, observational estimates of the decline in sea ice extent. And then all the other coloured members are from CMIC 6 models, trying to represent that sea ice extent. But the models are relatively consistent with the observations over this period, although obviously there's a large spread there. Oh, this is the consequence is that Svalbard, where we did our field campaign, has basically no sea ice around it in summer anymore. In fact, it's 200 kilometers further north off the northern coast of Svalbard. So that is only in the last couple of decades that that's occurred. So this polar bear we actually saw during the field campaign, it was on the other side of the fjord, but obviously investigating a cabin, no ice around there. So this graphic was put together by Jake Aylmer, who is working on the sea ice part of the project. It's quite a nice illustration of the change in the sea ice edge during September, and then also the blue shading is the extent in September 2022 at the end of our field campaign. So you can see how in the year that we did the field campaign, sorry, let me just turn on the laser pointer. This is Svalbard here in the kind of Atlantic sector of the Arctic. You can see how in summer, even at the minimum extent, the ice used to extend to the east side of Svalbard and around the northern coast, and gradually it's gone further forward. And in 2022, it's quite a long way forwards by September, although in August it was more or less where these coloured lines are. And then obviously there's an extension of the ice down the east side of Greenland, partly because the ocean currents are out of the Arctic there. You can see how that there's been such a massive change in the sea ice distribution all around the margins of the Arctic Ocean basin. So this was a real motivation. I mean, basically, as a result of warming climate and a reduction in the sea ice extent, also earlier in the year, the sea ice is much thinner. So that means it's more readily moved around by winds, by wind forcing. It's also broken up by waves that are caused by cyclones blowing over the ocean, neighboring ocean, and then those waves going into the ice. And so that means it's much more mobile than it was previously. It's also in the marginal ice zone where there's partial ice fraction, the surface is actually rougher because of the edges of ice flows and so on. So this is a well-known characteristic. That means that the surface drag on the atmosphere is actually higher over the marginal ice zone than it is in the surroundings. So we did wonder whether that has consequences for the weather systems, for example, and changes in the weather systems in the future. Also, most of the campaigns so far have really focused on the influence of the atmosphere on the sea ice rather than the dynamics of the cyclones themselves. So we're really focused on the atmospheric dynamics and the influence of this lower boundary, which could itself be dynamic. So I mentioned already the importance of the friction. So this graph on the right really shows that as you vary sea ice fraction, there's a maximum in drag coefficient when the sea ice fraction is like kind of midway, whereas 1 would be pack ice. 0 is obviously open ocean. Those dots and bars were kind of observational estimates from various works, actually. But then the effects of friction on cyclones are also quite uncertain. So people often refer to the Ekman pumping or Ekman spin down mechanism, which is really one which refers to the dynamics of a barotropic vortex, so one that doesn't tilt with height. But actually these cyclones are highly baroclinic, and friction is more complicated than that when it comes to interaction with a baroclinic weather system. So we definitely wanted to investigate that. So there's the role of the sea ice. The surface heat fluxes are typically into the ice because the lower atmosphere is warmer than the ice in summer. So they're cooling from the bottom. And some Arctic cyclones also very long-lived. They might last even more than a month in some cases, which would be inconceivable for kind of mid-latitude cyclones. So just carrying on with that motivation, Jake was doing some work doing sea ice modeling and looking at very rapid ice loss events. So it's been hypothesized in the literature that Arctic cyclones are really important in these rapid ice loss events. So that here we're talking about timescales of days, maybe a week or so, when there's large regional changes in ice cover. That's faster than normally comes about through melting and so on. It's a real challenge for operational coupled forecasts, and increasingly operational centres are running their short range and extended range forecasts fully coupled. So, for example, Met Norway, the SMWF and the Met Office are all fully coupled these days. But there's very little data to evaluate those coupled forecasts, and in particular, how they're coupled. So that was another motivation for doing a field campaign. And the mechanisms for the influence of cyclones on that sea ice are poorly understood. So Jake was working with a well-known sea ice model called SICE. They call it SICE Plus, this particular version, because it's got a lot more parameterizations in than the standard. And in particular, it has the role of ocean wave breakup of ice. It has a variable form drag related to the sea ice fraction and various other parameters. It has a kind of statistical flow size distribution, like a kind of fractal distribution. And it also deals with melt ponds on the ice. All of these are really important in summer. But I just wanted to illustrate that actually these models are reasonably good on a kind of regional scale. So on the right are some observations of changes in sea ice fraction over a 1-week window from 2018. So the right-hand picture is from a satellite estimate. And where it's blue, the ice is extended, so the sea ice fraction is increased, and where it's red, it's decreased. And then on the left is a simulation of that using the SICE model. Because the models take quite a long time to spin up, actually these models are started years in advance and then run through a historical period and then into the period of interest, because spin up is substantial. So it's quite impressive that you can get a reasonable distribution like that. And then in the next picture, I'm going to show a couple of cyclones moving into the Arctic that were linked with this pattern. So here we go. Here's one coming in to Svalbard, and then another one starting on the north side of Svalbard. So kind of a large low pressure center just split into two cyclones, actually. But you can see how, it will loop round again, you can see how as the cyclone passes through the region of the ice, in fact, these two systems, basically the ice is transported by the wind, so it's extending on the Greenland side, on this side here in the Fram Strait, and it's decreasing on the right-hand side. So that's an obvious kind of signature of wind forcing of the ice. But actually, cases like this are quite hard to find. I mean, often it's more complicated than that. For example, you might just get an enhanced rate of melting to do with transport of warm air, warm cloudy air over ice, for example, preventing radiative cooling and therefore, warming the ice surface. So there are lots of mechanisms. And in fact, in Jake's work, which I'm not presenting here, he found that he could partition thermodynamic and dynamic influence on the ice. And only the dynamic influence was directly attributable to cyclones. So now thinking about the cyclone structures, that these are the kind of things that we're dealing with, and then I'll talk a bit about their dynamics. So these are two cases that we started off looking at in 2020. mainly because that's when the project started. So case A was one that we identified as kind of low-level dominant. So it has a warm sector here. The colors show theta E or theta at low levels. So we've got a warm sector here, and then there's slightly warmer air cut off in the middle of the cyclone, cold air wrapping around from the northeast. It's quite a small scale cyclone. And then the orange shows the upper level structure. I think it's theta on PV2, I can't quite remember. But anyway, we've got a trough here and a ridge on that side. So you can see how it's wrapping around low levels and upper levels. So that development is like a baroclinic wave development, and it's quite similar to mid-latitude cyclone. But in contrast, this one in July of the same year basically has an upper level cutoff vortex, and that's the kind of thing that's called a tropopause polar vortex. And it has cold air directly underneath where the low pressure center is. So that, in fact, vorticity increases with height. So in thermal wind balance of that, we have a cold core. We called it a columnar vortex structure because it's basically tall. You know, the positive vorticity is stacked up throughout the height. And this really has no counterpart in the mid-latitudes. And they have this kind of structure when they're a long way from any jet, for example. There's not a lot to disturb them up there. So back to the baroclinic waves. I mean, these are some pictures from that I produced more recently, but they're from the classic LC1 and LC2 life cycle experiments, just run at higher resolution. So the colors in the background just show near surface potential temperature. So pink's obviously warm. So for example, in LC2, you've got warm air wrapping into a kind of warm seclusion. And then the contours are the upper level theta on the tropopause. So, you know, they're wrapping around each other in this cyclonic wave breaking type of cyclone. In LC1, you start with cyclonic wrapping, but actually the whole thing extends and breaks anticyclonically later in the life cycle, particularly at upper levels. This type of cyclone looks a bit more like the Shapiro-Kaiser type of cyclone with a kind of T-bone frontal structure and a strong bent back front, if you're familiar with that. Whereas this is more like a classic Norwegian model with a warm and cold front meeting in a long occluded front going around here. So the Arctic cyclones we've looked at, even if they're low-level dominant on a baroclinic zone, they look much more like this kind of cyclonic wave-breaking type typically. We don't see much that looks like LC1. And that's also true to some extent in mid-latitudes in summer. So back in 2012, we did some flight campaigns over the UK looking at mesoscale structures within cyclones. And in fact, we had a winter campaign, a spring and a summer, actually. But this was a great summer case. You can see it's obviously got very dry air here in the black, where, you know, you can see lower down in the atmosphere through the dry air, and then these actually deep convection here and in the warm moist air wrapping around each other. So this was an unusually vigorous cyclone for summer in the area of the UK. You can kind of see the British Isles and France underneath there on the map. And then this is the radar at the same time. So for example, you can pick out a very strong line of convection here in the middle of that warm conveyor belt. So it's certainly a cyclonic wrapping kind of baroclinic system. And this was a schematic that was created by Chris Dearden at the time. So again, with the warm and the cold fronts merging into this kind of occluded bent back front. And a strong cold conveyor belt being indicated here on the cold side north of this front. And then this was another case in the same summer. This was also over Scotland. Obviously, the map's not shown here, but it definitely wasn't Arctic. This was Scotland. But it's a case where the the fronts have occluded, but the warm air has run quite a long way east of the cyclone center. So the cyclone low pressure center is left behind over here to the west, and the warm air is disappearing off to the east. So you end up with this really kind of elongated area where actually the air is moving westwards beneath the frontal surface. And what I'll show you later in the field campaign is this is a really typical structure for the Arctic cyclones in summer. So actually, it's not just Arctic in summer, also mid-latitudes in summer has similar kind of systems. And I think part of the reason for the structure is they have quite slow phase speeds, and that has a big influence on the structures. But neither of those baroclinic cyclones are anything like these long-lived columnar vortices. So this is a famous case, the Great Arctic Cyclone of 2012. This is a satellite image. You can just about make it out. Obviously, we've got cloud over ice here, which is a little bit of a challenge for remote sensing, but you can make out a very large-scale cyclone here. You can just see this is the whole Arctic Ocean basin. There's Svalbard at the bottom. And then this is the grey dots here at a track obtained from era 5. So you can see how it had an origin over Russia, but then it tracked into the Arctic Ocean basin where it lived for a very long time and did a couple of these loops here, right, quite close to the pole. And that's not atypical, but this kind of behavior doesn't happen every year. So then I'll show a couple more pictures kind of connecting with the tropopause level structure here. So this is actually from summer 2022 when we did our field campaign. So the picture on the left, you can make out Africa and obviously Florida there, for example, in North America. So here we're going right down to 25 north. And so you can see, I'm sorry, the diagnostic is geopotential height on the dynamical tropopause. So where it's white, the tropopause is low, maybe even as low as 5 kilometers. And then where it's blue, it's, in the subtropics, it's 14, 15 kilometers. So you've got a very strong subtropical jet here, and the North Atlantic jet, where we've actually got this ridge extending in the North Atlantic. So the jet's quite a long way north at this time. And then where I've marked a T, this is where there's a kind of tropopause polar vortex that's about to develop in that region. And then if we zoom into the Arctic region, so now you can see Iceland and Greenland here. So we've zoomed in a long way. This is the object T. But actually you can see there's a lot of other smaller mesoscale vortices where the tropopause is lower. So these are all these tropopause polar vortices. And the key thing here is that they're all in this region. They're a long way from any of the strong jets. In this region, it almost looks like geophysical fluid dynamics kind of turbulence. We get a lot of things rolling up. Also, things happen quite rapidly. So this is the 16th of August. On the 20th of August, we've actually got a much larger scale TPV right in the middle, just to the north of Svalbard. So this is one of the cases that we examined in the field campaign. So you might wonder how you get to that from this. Actually, we think that vortex merger is quite important, which is really interesting. It's quite hard to find, good cases of this in the mid-latitudes, but it seems to be quite prevalent in the Arctic. So it's an interesting bit of dynamics. You can also see this is only 4 days, and the whole scene across the Arctic looks really rather different. Whereas if you look in the subtropical jet hasn't moved over those 4 days, and we've still got the same ridge here in the Atlantic as well. So in fact, the mid-latitudes are evolving quite slowly compared with what's going on in the Arctic. If you like these plots, you can find them here at this link. So Ben Harvey produces these daily from operational ECMWF analyses, and we produce these tropopause maps. It should be there the whole time. Sometimes we have breaks in the data feed from the ECMWF. But yeah, I encourage you to have a look at that. So now I'm going to talk a bit about the climatological work. So where we're really comparing the tropopause polar vortices, or TPVs, and the low-level Arctic cyclones. So to start with, an important factor is that the meridional gradient in temperature is really strong in summer around the edge of the Arctic Ocean. That's because there's just a big land-sea contrast. So the ice is relatively cold and the land surface warms up enormously in the summer. You know, in bits of Siberia, surface temperature maximums can get up to 50 Celsius, which is incredible because in winter there'll be minus 50 Celsius, you know, so pretty extreme place. And so you get some very strong gradients around here. And if you look at the track density of Arctic cyclones, there's a maximum kind of around this coast where we've got strong baroclinicity. There's also, you know, obviously across Alaska and into the Canadian archipelago. But the density maximum is really around this part of the Russian Arctic. And if you look at Genesis density, that's even more focused on the Arctic frontal zone. So this is all of the tracks which can wander into the central Arctic, but the Genesis is really around the edges and on the eastern side of Greenland, which is for different reasons, actually, not so much the temperature gradients, but more Lee cyclogenesis. Then this is at the tropopause level, the TPVs. So the genesis there is not so much on the Arctic frontal zone, and in fact, there's a lot more going on around the North American side of the Arctic. And in particular, if you look at the track density, they do hang around much more on the Canadian Arctic there. So yeah, we'll come back to this. So this is a climatology that was published a few years ago by Sue Gray and some others of us in Reading. So then what we did in that paper is we looked at Arctic cyclones, and then we found the ones that were matched or unmatched with a TPV, just done by the proximity of a TPV at the time of maximum growth rate of the surface cyclone. So the question was whether a TPV was related to the growth of the cyclone or not. And in fact, if you look at the unmatched ones, these are basically then low-level dominant cyclones. You can see they're really focused on the Russian side of the Arctic. And the ones matched with TPVs are really over the Canadian side and the North American side. So there's quite a striking variability across the Arctic there. And then these are composite structures for those two types. So on the case, we've got the unmatched one, and then the times are running downwards. So we've got 1 day before maximum growth rate on the top row, then maximum growth rate, and then maximum intensity. So you can see as the cyclone develops, the warm sector gets stronger. It's kind of wrapping around the east side of the cyclone. Obviously, the surface pressure minimum is decreasing. And then at maximum intensity, the surface pressure minimum is the deepest. And then if you look at the vertical cross-section here, we start off with vorticity strongest in the lower troposphere. There's a westward tilt with height during maximum growth. I say westwards, actually, the orientation of this is that the cyclone translation vector is always to the right on these diagrams. So when I say westward, I mean upshear, I backwards relative to the motion of the low-level cyclone. So this is a baroclinic tilt. And then you can see maximum intensity, it's essentially become untilted. And then in the ones matched with a TPV, unsurprisingly, there's a larger vorticity initially at tropopause level. There's the kind of upshear tilts during maximum growth, and then even by maximum intensity, it's still upper level dominant and untilted. So this led us to introduce a cyclone phase space. So in a cyclone phase space, it's a bit like the Hart phase space, but we changed the variables a bit so that they're non-dimensional. So the idea is that one of them characterizes the thermal asymmetry between the warm sector and the cold sector, but we non-dimensionalize it so that we would expect the values to be in the range 0 to 1 if it was like in the quasi-geostrophic regime. And then the thermal wind is characterized by the thermal Rossby number, which is basically the baroclinic relative vorticity divided by the planetary vorticity. And that turns out in thermal wind balance, it's just related to how warm is the core relative to the environment of the vortex. And you can see that we've got the same constant parameters multiplying both of these. So both of these essentially lie in the range 0 to 1. We also didn't use the storm motion vector to define the right and left side of the cyclone. That's because these Arctic cyclones do all sorts of loops, and basically the warm sectors does not relate very clearly to the direction of motion. And so we just found the maximum contrast between two sides of the cyclone to get this diagnostic. And then we attain a plot like this. So the thermal Rossby number is along the x-axis. So then the right-hand side is warm core, and the left-hand side is cold core. And then the thermal asymmetry parameter is this B, or you could call it baroclinicity. But high values have a strong warm sector, low values are kind of more symmetric, axisymmetric. So for example, if you looked at the Great Arctic Cyclone, is its green trajectory, the genesis is down here, basically, but then it went up here to a very high baroclinicity. So the maximum growth rate is typically when the baroclinicity is highest. And then it actually transitioned, it came right down here to the cold core symmetric structure. So these are these tall columnar vortices. And then the background shading is the density of all cyclone tracks. So you can see that they spend most time down here. And this is always the later stages of the cyclones, these cold core vortices. And then the case A we saw from 2020 was the low-level warm core. So it was warm core initially, but ended up cold core. And then we had the one that was basically a tall vortex the whole time. So it was cold core the whole time, even during maximum growth. So in fact, here we classify the cyclones into two types, just basically on whether they're upper level dominant or lower level dominant at the time of maximum growth rate. Because you can still have baroclinic growth. All this tells you is whether the vorticity is larger at the top or the bottom. So you could think of it as upper level lead or lower level lead development. So, but the important point here is that if we, by definition, at the time of maximum growth, we have to be on the right-hand side of the zero line, but the trajectories are such that they don't stray into the left-hand side. They basically go through the crosshairs here and end up in the cold core symmetric. So that's a typical trajectory. Whereas for the ones that are upper level dominant the whole time, they just stay on the left-hand side of zero and just they lose the warm core essentially and become untilted. So we classify those as two types of Arctic cyclones. So that classification then becomes very important when we think about the effects of friction. So I'll try and explain this now. So the potential vorticity is the quantity we're interested in here. Hopefully, many of you are familiar with that. So kind of absolute vorticity dot product with the gradients of potential temperature. And that quantity is conserved in adiabatic and frictionless flows, but when we have friction, it's not conserved. So in particular, we have this term here related to the curl of the frictional force F. And there are various ways of looking at this, but Cooper, Thorpe, and Bishop, quite a long time ago now, did change this by taking a vertical integral of the Lagrangian PV tendency over the boundary layer. So like a boundary layer average PV equation. And it turns out, under certain approximations, that this splits into two terms. One looks like Ekman friction, which is related to the wind stress curl, essentially. Small h here is the boundary layer height. The other one is not to do with Ekman. It's called baroclinic or PV generation or frictional baroclinic PV generation. So it still depends on the surface stress, but it requires also a horizontal temperature gradient. So this picture here comes from Benoit Vanier's paper, where he looked at composites of mid-latitude cyclones. So you can see actually these two terms have the opposite signs. So the Ekman friction typically is decreasing PV, and you can think of that as the spin down of a barotropic vortex. Whereas the baroclinic generation term typically is generating PV in the region of the warm front. Yeah, and we'll explain why that is in a minute. So this is often described as like amplifying mid-latitude cyclones. So then we looked at the same things in these two types of cyclones by focusing on those two case studies in 2020. So remember, this one's cold core and tall, and this one's low-level baroclinic. So if you look at these terms, now we've got Ekman friction on the top row and the baroclinic PV generation on the bottom row. So in cyclone A, which is the low-level dominant, the Ekman friction is negative in the middle, and the baroclinic PV generation is positive. So that looks a bit like a mid-latitude case, and it's you can see it's quite a small-scale cyclone here. But in the tall upper-level dominant one, basically both Ekman friction and baroclinic PV generation are negative. So that means PV is decreasing in the boundary layer. So the sign of this baroclinic term depends on the cyclone structure. So then if we integrate that in a radius around the cyclone center, so we've got time running along the x-axis, and then this boundary layer average PV tendency. You can see the baroclinic generation is strongly positive in the low-level dominant case and opposing Ekman friction until the time of maximum intensity is this bold grey line. After that, the baroclinic generation goes because it's no longer baroclinic. It's basically tall and a tall column vortex. Whereas in cyclone B, the baroclinic generation is actually negative quite early on, and it's much stronger than the Ekman friction. So this has quite important effects. Oh. So in fact, the way we understand this is kind of summarized in this diagram here. So first of all, this baroclinic generation term can be written as a dot product of the surface stress and the thermal wind vector across the boundary layer into the lower troposphere. So in the low-level dominant case, typically we have a low-level center here with a warm sector. The thermal wind is along the isotherms to the east there, whereas the surface wind is going around the cyclone and also slightly turned in towards the cyclone center due to frictional turning. So there's a very large angle between them. That means that this dot product is negative, and we actually end up producing positive PV. Whereas in the cold core case, the surface wind is in a similar direction, but the thermal wind is actually like this. So actually the angle between them is small. So the sign of this dot product is the opposite. So here we're decreasing PV. But also what we find is that the cold core structure, the temperature anomaly basically amplifies as the low-level vortex decays. So that's a consequence of thermal wind balance. So the vorticity gradient increases with height, and that gets stronger. That means it's got a stronger cold core. And at the same time, we're also cooling the bottom of the cyclone. So we think this probably contributes to the longevity of these tall structures that last for many days. In contrast, in the low-level dominant cases, the friction basically removes the low-level warm anomaly and the cyclone. So these are going to decay more quickly as a result of friction. So in the time I've got remaining, I'm going to show you some highlights of the field campaign. So the list of authors here it's basically the list of authors on a BAMS article that we submitted back in January. So Gwendal Riviere and Paris has led this. So Gwendal and Julien Delano basically had funding from the Naval Research Labs to do a field campaign with the French aircraft on behalf of the ONR Arctic Prediction Program, and then we joined up with them. So the objectives were to fly these two aircraft. The UK aircraft is this British Antarctic Survey Twin Otter, and it flies at low levels and can measure surface fluxes and also the ice surface underneath. So in particular, we can measure very high resolution topography of the ice, so even flows and roughness elements and so on. We can measure surface temperature with an infrared thermometer. We can measure albedo from the shortwave radiation measurements. And all of these are very high resolution, so effectively like kind of 2 meter scale underneath the aircraft. We measure the near surface turbulent fluxes by flying within the flux layer. So typically we have to fly at about 70 feet above the ice, which is very low when you're in the plane, I can tell you. And then the Sapphire aircraft was flying in the mid-troposphere, but with Doppler radar and LiDAR. So they can use that to measure wind curtains in both cloudy and clear air, as well as the cloud, liquid, and ice. So this is a kind of unprecedented set of observations for Arctic cyclone structure. So this is just a picture of the Twin Otter. You can see the various instruments, but it's quite a small aircraft. They spend most of the time in the Antarctic, in the Antarctic summer, but we were able to use it in the Arctic for this field campaign. Inside, it's quite small. It's not a very big aircraft. So the mission scientists sit here in these 2 seats in front of that computer screen. And then that person there is just standing in the doorway to the cockpit. So yeah, there's not many people on this plane. This is actually the extended range fuel tank, which is always a little bit disconcerting. And then this is what it looks like in the cockpit. So this is the pilot there, and then that's me in the mission scientist seat. You don't have a lot of space, not a lot of leg room actually, and you have a laptop on your knee, which has the output from the science instruments, whereas this is all navigation stuff. And in fact, here we go. They've got this kind of, you can see quite a few parameters at once as you're flying around. And as I say, then the ATR aircraft was really focusing on the remote sensing with the radar and LiDAR, as well as a lot of cloud physics instrumentation. So this is a much larger aircraft run by the Sapphire facility. And we were very lucky. I mean, in fact, we tried to go in 2021 originally, but we couldn't get to Svalbard because of COVID restrictions. So then we delayed to 2022. But in event, it was just very lucky because we actually had 4 Arctic cyclones during our field campaign period, which was, much better than we might have expected. And also the ice was quite a long way away, but not as far away as it was in 2021. So you can see the average ice distribution over the field campaign here. So with the Twin Otter aircraft, we spent a lot of time trying to go to the ice edge at low levels, which is why all the flights are focused around there. The ATR-42 was not trying to fly over ice. They were trying to fly through the warm conveyor belts and low cold conveyor belt jets and things like that. Also, they're obviously very interested in the cloud structure in these cyclones, whereas we were trying to measure turbulent fluxes in the ice surface, which is why we were focused on the ice side. We also flew over to Cape Nord on Greenland here to get more time over ice. So in fact, you can see we had different objectives. So these are flights measuring turbulent fluxes over the ice. These are all cases in Arctic cyclones. And then we had a few other objectives related to low-level tip jets and so on. You can also see with a small aircraft, it's quite challenging to reach the ice. This is a signature of Arctic change because any 20 years ago, this ice would have always been literally on the coast here. So it just shows how far away it's moved. So this is what it's like flying low over the ice. The aircraft isn't quite as bouncy as it looks. That's because I couldn't hold my mobile phone still. But yeah, you can see that the ice has a lot of melt ponds on it, which are the pale blue. And then in some regions, you can see there's a large lead ahead, if you can make it out, the kind of darker blue on the horizon there. And then on the bottom left, this is the very northern tip of Greenland with these black cliffs. So this is a glacier on the left, and this is just sea ice. This is a large lead that just opened up. And then on the right, this is to the north of Svalbard. So this is another region where the ice has a very different characteristic, much more broken up in terms of ice flows and so on. Station Nord's very lucky to go there. It's a very odd place. It's like a petrol station for light aircraft in 2,000 kilometers from anybody else. It's really, really very isolated, but only 933 kilometers from the North Pole. And you can see, you know, it's basically all gravel there. So the runway is gravel as well. So this is just landing as we arrived. So it's here on this little bit that's not ice covered, but this is all then permanent sea ice, and this is a glacier behind. So these are the 4 cases. This is why we are so lucky. So Svalbard's here in the middle. The first case is this grey track. The second one was this orange track here. It's actually a strange low pressure center that split into 2. So this other orange track was in the same low pressure center, but a different vorticity center. The third one went right up here. In fact, it tracked right next to the pole and lasted many days, 12 days, in fact. So this became an untilted columnar vortex. So it was really lucky we got one of those cases. These ones down here tended to stay more baroclinic. So the fourth one was quite a strong system with very strong winds into northern Norway. In fact, these 2 pictures are both of Cyclone 3, but in its warm core growth phase to the southwest of Svalbard, and then in its cold core stage when it's actually north of Svalbard there. So a bit about Cyclone 1. So this is a very weak cyclone, so mean solar pressure is shown in there, but actually you still had a substantial amount of precipitation with it. So the blue here is precipitation in the model. So this is the Met Office model, actually. It's the global model. You can see that there's the warm sectors right over here to the east, and then it's wrapping around in the warmer air. So both aircraft are flying here along 29 east, you know, doing cloud physics measurements. And then you can see at upper levels, this is potential vorticity in the upper troposphere. You can see that actually it was a coupled development, but just really quite relatively small in scale. And actually upper level dominant. I mean, this vorticity anomaly here is stronger than the low level vorticity anomaly. Then this gives you some idea of the cloud physics measurements. So it's really impressive. So these legs here are crossing the same main precipitation band 3 times, but just at different levels. So you can see how the aircraft is stepping down here. And so the idea is to measure the clouds with in situ measurements and also the radar LiDAR combination. So the top panel is the radar data. It's upward and downward pointing as well. So that's why we can see above and below the aircraft track. This is the LiDAR, which was only downward pointing, as you can see from the data. But it can't see through these layers of supercooled water and ice. So you can see it's attenuated, so there's no signal below those. But by flying at different levels, they can deduce the cloud type. So this is quite remarkable. So it turns out there are multiple layers of supercooled liquid water interleaved in the ice clouds. Where the updraft's strongest, it's just ice. And then the blue at the bottom is cold rain, which is below the melting layer. So this kind of thing has never been observed directly before in these Arctic cyclones. So they're very excited about that. And in fact, the in situ data then shows you the variety of ice crystal habits at the different levels we're flying here. And in fact, this will have been mainly a supercooled liquid layer in this layer. So these are actually little droplets, but still some ice probably falling from above in those layers. Whereas these are aggregates. And then actually on the lowest layer, we've got a lot of these ice needles. So very interesting. So cyclone 2, we focus really on the winds here. So this was a much stronger cyclone case. This is the mean sea level pressure, and the shading shows where the wind speed is above some threshold. So there were strong winds here going towards the west. This is in the kind of cold conveyor belt flow on the north side of the warm air. You can see it's obviously low level warm core because we've got this warm air cut off in the middle of the low pressure system. Then we've got pretty strong winds into the Norwegian north coast down on this side. So we did both flights here. This is both aircraft at the same time in this region. And then at upper levels, we can see there was an upper level PV anomaly. And in fact, this is an exit of the jet. So the jet over the Atlantic was a very long way north at this time. And so this system actually developed on the left jet exit. So it's definitely a baroclinic system. And then here's a sample of the observations. So the ATR flight track of relevance here is this AB section. So this produced this Doppler wind section. So this is actually observation only estimate of the wind speed. And you can see that we've got this sloping interface there. And then above, we've got the Met Office model. So the potential temperature shows you, obviously, it's a sloping frontal surface. So it's this occluded, well, in fact, it's a bent back front. And the higher wind speeds are underneath the frontal surface, so very low level. They tend to be underestimated in the model. So if you do a long flight comparison, time series comparison, you can see how the observations are quite a bit higher than the model estimate in blue. So the observations in red, the model in blue. In fact, by typically 5 meters per second on average. And we found that this was also true in other low-level jet cases. So the low-level winds are pretty strong in these systems, even though they don't look like very strong cyclones. The low-level winds are pretty strong, and then you can imagine that they have quite a big impact, not just on ice, but also on ocean traffic and all sorts of things here. So we did this more zigzaggy track because we were going upwards on a stack of levels across the front. And in fact, we want to use this case to look at the baroclinic frictional PV generation because we're measuring turbulent fluxes on each of these legs in situ, and then we have the information about the vertical and horizontal gradients. So we've got enough information to actually estimate baroclinic frictional PV generation from this section, but we haven't done that yet. And then this is the really exciting case. Sorry, it's a very slow animation here. Just shows the evolution. So cyclone 3 is this one here that ends up to the north of Svalbard with a cold core. But the move, it starts down here. So here it is, it's developing as a baroclinic system here with an obvious warm sector. And then it does a transition over Svalbard into something with a cold core. So we've got some very cold air here that's come directly across the pole into that system. And then at upper levels, you can see that there's a tropopause polar vortex. And that ends up directly above the low pressure center by the end of the animation there. So this sequence is, the 14th to the 20th of August, so about a week, shows the transition from baroclinic growth into the cold core case. And we had a lot of flights in this with both aircraft over all the stages. So that's a really exciting opportunity. And I'm just going to show you towards the end here. These flights on the 19th and 20th was when the cyclone is now to the north of Svalbard and has this very cold air down the west side of the cyclone. So the cyclone's here, and the French aircraft flew across towards Greenland there, basically able to measure the structure of the tropopause polar vortex above and the surface cyclone below and the clouds associated with that. Whereas we had to fly to fly low over the sea ice, we had to be in clear air because you can't fly low in cloudy air. So this is why we were quite a lot further south, but just about over the ice here. But still where the very cold air is coming from the pole in strong winds. And then on the following day, we flew again to the sea ice edge, just to the south of the cold air outbreak. This shows you the level of detail that you go to. So this is the same time as this flight here. So it's hard to imagine how much detail there is in the ice until you see the satellite image. So these curious structures are formed by, well, we don't know exactly how they're formed, but we think it's a combination of ocean eddies, because there's a northerly flow of water along the ice edge here. So it's probably sheer instability in the water, but also maybe some ice forcing by the atmosphere, I'm not sure. And then you can see there's so much structure in the flows. And then the dots are surface temperatures averaged along the track on the aircraft. So you can see basically it was about 0 Celsius. That's important because actually the European Centre model on the ERA reanalysis has a known bias. It's typically about plus 1.5 Celsius in ERA data. It should be 0 essentially, and these observations show that quite clearly as the ice is melting in the situation. This is actually a photo taken from point P here. So you can see there's a real heterogeneous mix of melt ponds and leads, all sorts of roughness elements. And this is just a histogram of albedo from this section of flight. So you can see how much variability there is in albedo. So in the current models, this whole region would just have one value of albedo. So it really doesn't reflect what's there. So the forecasting centers are particularly interested in this albedo information. So I've covered a lot of things there, but I hope it gives you a flavor of what's really interesting with these Arctic cyclones. So just in summary, there they often grow far from a jet stream, although their early growth phase is typically baroclinic, and often they grow in this Arctic frontal zone where there's a large temperature gradient at low levels. But they don't have to. They can develop from a pre-existing tropopause polar vortex as a kind of top-down development. And so that leads us into 2 distinct types of Arctic cyclones. The first type is quite similar to mid-latitudes. The second type really has no mid-latitude counterparts. And these both of them end up as upper-level dominant kind of tall vortices, and they can last many days like that. And we've shown that the friction acts differently on these 2 cyclone types, and we think that action actually tends to encourage them to become upper-level dominant columnar vortices. So friction is playing an important role here. And then I've shown you some highlights of the field campaign, but we've just got so much to do to analyze the findings from that field campaign. So at the moment, we're focusing on the measurements of the sea ice surface and in relation to the positions of the cyclones, but also looking at Arctic cyclone dynamics and using potential vorticity tracers, which kind of enables to link the structure to the processes that are acting in these cases. So I'll leave it there and invite any questions.
Great. So yeah, let me start with just the first question. Yeah, thanks for this really interesting presentation. So you mentioned that there are sort of one of the cases that you showed is kind of a small vortex like and then developing into a much bigger vortex, and you mentioned that it's likely due to vortex mergers. So
Yeah.
my question is that how well do our reanalysis actually capture those vortex merging event, or how well do we actually predict them, this kind of vortex merging in models?
Well, that's a good question. So actually, during the field campaign, we weren't close enough to any of those merger events to observe them directly. So because the we were lucky enough to get 4 cyclones, but none of those were involved in a merger near Svalbard. So unfortunately, I can't answer the question on how realistic the analysis is. But I guess it ties in with satellite imagery quite well, because when there are tropopause polar vortices, you can see whether there are, with water vapor imagery, you can see these things. But in terms of predictability, we were finding in the campaign actually the range of predictability can be quite short. In fact, that was a real challenge forecasting, because even 2 days ahead, we'd have to change our plans substantially because the situation changed very rapidly in the forecast. More so than, for example, when we were doing the Nordex experiment in the mid latitudes. So yeah, I found that very challenging. I think it's partly because it's so small scale, a lot of these interactions in comparison with mid-latitude systems.
Okay, yeah. I think Shep, you have a raised hand.
I really enjoyed that tremendous amount of information to
Yeah.
assimilate it. And I'm a chemist, not a meteorologist, so my question comes from that perspective. But you mentioned in the beginning about the impact of Arctic cyclones on the sea ice structure and moving ice around and breaking up the ice and so on. And I'm wondering, what you've learned or to what extent the interaction goes the other way. To what extent do the surface characteristics impact the trajectory of the cyclone and its strength and so on? And when simulating, to what extent do you need a resolution in the model that can capture the surface heterogeneity? In the end there, you showed what we know the Arctic looks like in the summertime, extremely heterogeneous. So does it matter?
Yeah, no, that's a good question. And in fact, that's what we were investigating, particularly before the field campaign, by looking at the European Centre and the Met Office coupled prediction systems. In fact, we had, at that time, the ECMWF operational prediction was coupled, but we ran a parallel suite where the ice distribution was made to be static in each forecast. And then we also ran another one where we changed the coupling so that the surface temperature was coupled in a different way. And what we found is that those experiments had a big influence on the sea ice distribution, but actually hardly any influence on the track of Arctic cyclones or their structure. So they were actually quite insensitive to that. And that was also true in the Met Office model. But then a warning to us in a way was actually the nature of the changes was different in those 2 forecast systems. So actually in the Met Office model, the main influence is through a change in the boundary layer stability, which then changes the Ekman spiral, and that has an indirect effect on the surface winds through the difference vertical wind shear through the boundary layer. But in the ECMWF model, it seemed that the difference in the drag over the ice was more important than that stability effect. So it indicates to me that we don't know actually what the situation is in the real atmosphere, and it might well be that the coupling is more two-way in the atmosphere than it is in the current operational coupled models. But there are so few observations that are suitable for testing that. That's one of the main motivations for doing the field campaign. So now we're working with those centres to try and use that data in the 2022 period to kind of work out a bit more about that coupling. So I think it's just still an unknown, but in summary, in the current systems, the action of the surface on the cyclones themselves is weak, but I'm not sure that reflects the true nature of the beast. Yeah.
Thank you.
So Minghua?
Yes, thank you for this very interesting talk. You also have the best pictures from atmospheric dynamicist. I really enjoyed it. I have many questions, but I'm going to ask two to leave time for others.
Yes.
One is you showed this interesting cross-section, time and vertical cross-section of clouds from the radar. I wonder
Yes.
whether you had a chance to look at the same field from either ERA analysis or from the Met Office model to see how these like state-of-art analysis capture such cloud structures.
Yeah,
Maybe you can answer first.
I haven't yet. I mean, Julien Delano in France is the one who operates the radar lidar system, and he's definitely looking at that, and so the French team is looking at that. But yeah, well, that wasn't the focus of our project. So we were focusing more on the wind structure and the momentum fluxes and effective roughness. So we had kind of different emphases. I should also say that although we managed to do the field campaign, there weren't many people supported on that project. So the French team were essentially paid to deliver the field campaign, but they don't have anybody working on the analysis. So they're doing that with people who are like working on other things as well. So there's lots of opportunities there. And in fact, both data sets are available on open access. So the UK and the French data are on two separate databases, but they're both available to other researchers who are interested. So if you want to have a look at it, then please contact me and I can point you in the right direction.
Great. And then the second question is about the two types of cyclones. They are associated with different types of baroclinic zones. It looks like
Yes.
the low level and the upper level. Do you have any perspective regarding, say, future changes of these cyclones in the warmer climate, given the changes of the baroclinic zones in the polar region?
Yeah, well, so the low level development ones on the Arctic frontal zone, I think the projection is that the Arctic frontal zone will get stronger because we end up with higher temperature and humidity, so higher theta E over the continents, and even though the sea ice extent is reducing in September, it's at least in the near future, there's going to be ice throughout most of the summer, so definitely the Arctic Ocean area is colder than so we'd expect the Arctic frontal zone to get stronger. I guess that's the kind of thing that would be different in a much longer term projection. If there were no ice at all, then that would be a different thing, I think.
And what about the upper level?
Well, the upper level, I really don't know actually, because I'm not sure what the influence of climate change might be on tropopause polar vortices, and in fact, they're almost things that exist in the absence of other things going on. You know, it's because they're a long way from jets that are in thermal imbalance and things like that. So it's just it's almost like quasi-geostrophic turbulence. It's just, and I think that's why merger can happen, because there's not a lot else to disturb them, really. But I think that's an interesting topic on its own, you know, kind of more theoretical topic.
Yeah, that's right, because then they have implications on the surface sea ice, right? And therefore the surface albedo feedback.
Yeah, that's right. And also I think that's why in some summers we end up with one very strong cyclone that lasts for a long time, because I think that it has probably merged with some other smaller systems. And there's a nice paper by Yamagami, kind of Japanese author, who shows summer in 2016 was quite like that, with a number of systems coming from mid-latitudes into the Arctic and kind of merging, kind of going upscale. They're really interesting dynamics, yeah.
Thank you.
So, Brian?
Yes, hi. Hi, John. I really enjoyed the talk. I also enjoyed the fact that you looked at this from a PV perspective, obviously, and doing kind of a PV budget baroclinic and and the friction. And one thing that I thought was interesting, or is I'm not sure why you also didn't look at some of the other diabatic processes like latent heating or surface fluxes in that PV budget and how they relate, to the type A. It seems like with the ocean, there would be a fair amount of surface flux, and then latent heating, could add the vorticity at the bottom and destroy it at the top. And so how does those processes fit into?
Well, yeah, so we are looking at that now. But we're doing that on the cases that we observed in the field campaign. So in the Met Office model, we have these online diabatic tracers. So both potential temperature and potential vorticity, we have separate tracers that accumulate the effects of tendencies from different routines in the model. So we can pick apart the effects of boundary layer friction or latent heating from the large scale rain parameterization or the convection scheme if it's on. And in fact, we have convection permitting limited area simulations as well as global simulations. So that's all work that we're doing right now, actually, but I didn't have enough to show that. And we're kind of focusing actually on those fronts, mainly on the north side of the cyclones, mainly because that's where we took most of our observations as well. And that's also where the winds are strongest in these systems. So the wind maxima are really low level in these cyclones, which is also quite different from most mid-latitude systems, because there isn't really a strong jet nearby. I mean, all the action is quite low down.
Yeah, no, I'd be curious to learn more later, I guess, about the relative role of the latent heating, for example, and the baroclinic.
Yeah, that's right. I mean, yeah, and I think there's quite a bit of uncertainty in the representation of latent heating because of this ice. The mixed phase clouds we think they're not very well represented, but again, that's also work to do because it's really mixed, with all these interleaving layers. It's very complicated. But the one thing that's definitely true in the Arctic all the time is it's really highly stratified. So the boundary layer is very strongly stratified typically, and then above it is as well. And then the clouds are also in all these quite thin layers. So there's not a lot of strong mixing in the vertical most of the time.
Okay, thank you.
Okay, yeah, I think there are probably tons of questions, given that you've given us so much information and such a very interesting talk. But yeah, I'd like to thank you again for sort of giving us this presentation and a lot of new information about Arctic cyclones.
Yeah, no, it was a pleasure, and please do feel free to email me if you want to ask some more questions. I mean, that's open to anybody in the audience. Yeah, and yeah, I can send you the presentation as well. Oh, I think I was going to send it to you, Edmund, wasn't I think.
Okay, yeah, great. Sure.
Yeah, I got to see the Arctic ice in the summer without knowing anything before.
Yeah, no, I feel very privileged to have gone there. I mean, it's a fantastic experience. Yeah.
Okay, great. Thank you. Thanks a lot.
Okay, thank you very much. Okay, bye.
Bye.